Right, yeah, so we've got Newton's second law now. Okay, so Newton's second law of motion is probably the least well known, sort of just describing a relationship more than anything. And again, it links to the first and the third. Obviously, with inertia, we know that a greater force is needed to move a larger mass, which makes perfect sense. So it's linked to our first law there, and our second law, obviously, it helps us calculate the size of a force, a reaction force as well. So it's pretty important to know. Links very strongly to the first law, but my theory with this is probably easiest to go through a couple of examples of how we can use this law to our advantage and how we can show off how it's applicable in the real world. So the first question, I like to use Bob. So Bob kicks a 2 kilo ball. He's probably going to have a sore foot the next day, but he kicks it with 60 newtons. Calculate the acceleration of the ball. So I always like to write down my law. Okay, so that force equals mass times acceleration can be written as F equals ma. I identify straight up what variable I want to get, so I need to find the acceleration. So I want my a value. So to get to my a, I just need to get it by itself. So I divide both sides by m. I cancel the m's on the right hand side. You don't need to have your a by itself on the left, as long as it's by itself on one side, on the top. We're all good. So then my final equation should have a equals f divided by m. My force is 60 newtons. My acceleration is, my mass is 2 kilograms. I need to make sure I'm in standard units, so I get the 30 meters per second squared. That is a very, very high acceleration, but that's one of the applications for it. Okay, for number 2, this is again, we're applying the third and the second law together here. So we've got Bob has a mass of 80 kilograms. What's the size of his reaction force? The reaction force his chair is applying on Bob. So we want to know, just to make sure we're clear with our third law, we want to know the force it's applying upwards. Now we know, according to Newton's third law, every action has an equal and opposite reaction force. So we can calculate the force that Bob's applying on the chair, and whatever that force is will be exactly the same as the force that the chair is applying on Bob. So F equals ma. In this situation, we want to know the force. So we've already got it in the position that we want it, by itself on the top. F equals Bob's mass, it's pretty ordinary, equals 80 times the acceleration. I'm just going to approximate that Bob's on planet Earth because he hasn't got his spacesuit on. So I'm going to approximate that Bob's on Earth and just use 10 meters per second squared because I'm lazy and don't want to use 9.8, which gives me 800 newtons. So there is 800 newtons of force applying upwards. Now, as I said in the last video, we're heading towards doing free body diagrams, which are when we're taking into account a whole number of forces on an object, and Newton's second law applies particularly with those. It's really important to remember that force is a vector component, which means direction matters. Okay, so if you've got a force pushing one way and one pushing the other way, they're obviously going to cancel out. If you've got two forces pushing together, they're going to add together. So as we move towards free body diagrams, we'll get ready for that. But let's just start with a nice induction, I guess, towards that. So Bob's got it. So I always like to go through his problems and identify because I got a bit of information, so I identify the key information. Bob's car has a mass of 1,000 kilograms. Okay. If 800 newtons of and a motor that applies 7800, which is 7,800 newtons of force. Okay. If 800 newtons of friction, and this is important, the word friction is important, are present, what is the acceleration Bob's car experiences? So the word that I'm sort of looking for here is acceleration. So I need to find his acceleration. So with these problems, it's often a good idea to do a diagram. Once you get further through this, we won't be doing diagrams up, we'll just be drawing a box, and I might even draw a box here to represent our car. Our car has a mass of 1,000 kilograms. Let's just say that this is the direction the car is travelling, forward. That is 7,800 newtons at max. And in the blue is our friction. Our friction always applies in the opposite direction. Okay, so friction always applies against motion. So if we're driving forward with 7,800 newtons, the 800 newtons will be applying in reverse. What's the total force on that car? What's the net force? So F net. What's the total force on that car? Well, it's going to be a bigger force as they're applying in opposite directions. subtract our smaller force. So we've got 7,800 newtons minus 800 newtons equals 7,000 newtons, sorry. 7,000 newtons is our net force. Now with that, we can think of that now, it's just our overall force, because when we cancel those two out, it's almost like, and I'll do it in black, we've got a overall force of 7,000 newtons applying in there. F equals ma. I'm now looking for my acceleration, so I divide both sides by m. The m's cancel there. I've got A equals F, which is 7,000, divided by 1,000, which equals 7 meters per second squared. Now, for those of us that were in tune with our math class before, we were talking about assumptions. Okay, I've made some assumptions in solving this problem. Okay, one of the assumptions that I've made is that Bob is not in the car, and that's a pretty wild assumption. Okay, but I don't know Bob's mass, and Bob's mass is obviously going to affect the mass of the car. It'll affect the acceleration, therefore, and it might even affect the friction, as we'll learn later on. So it's pretty important to understand assumptions when we're making them. Newton's first, second, and third law, and be able to represent those in diagrams, subtract and add forces when appropriate. So hopefully you got the key takeaway with that. It's all about F equals ma, being able to rearrange that equation and put a quantity, which is a number, on the size of the force, acceleration, or mass present in a problem. Cool. Hope that helps.